Hey everyone, we're back talking about chi-square. This time we're talking about a chi-square test of independence. This is a chi-square where we have two samples. Really what we have is two dependent variables that are either measured at the nominal or ordinal level, or we fall back on a chi-square if we have done a parametric test and we violated an assumption and we just have to go to something else. So this chi-square test of independence sometimes is called a chi-square test of association. Sometimes people also call it a chi-square test of contingency table. So the example that we're going to work with is a study where the researcher wants to know whether there's a relationship between when a student reads their textbook and what grade they get in class. So we have two samples or two dependent variables: when you read and what grade you get in class. So when you read is a nominal level variable. You can read either before or after class. And the grade you get in class is ordinal. You either get a poor grade or you get a good grade. So 50 students were randomly selected. They were categorized into whether they read before or after class. And it was found that 26 read before, 24 read after, and then when they were done with the course, their grades determined where they kind of fell. And this put them into a table that is sometimes called a contingency table, also called a cross-tabulation table. This table really illustrates the degree to which grades are contingent on when they read the text, whether there's a relationship between those variables. So let's look at that crosstab or that contingency table. So I have these cells labeled A, B, C, and D, just so I can draw your attention to the cells. So what this shows you is that 20 students who read before the lecture got a high grade, and 6 students who read before the lecture got a low grade. So that adds up to 26 students total. And for reading after the lecture, 12 got a high grade and 12 got a low grade for 24. You can also add 20 and 12 to get 32 total who got a high grade, and 6 and 12 for 18 total who got a low grade. So these are the marginal frequencies, right? And we can add these two together to get 50 and these two together to get 50. So these are our frequencies. These are the observed data. So now we're at the point that we can actually do our statistical test. So we're going to go ahead and pick our test. We're comparing two groups. Really, we're just looking at two dependent variables to see if there's a difference or a relationship between them. They're measured at the nominal or ordinal level, so we know we can't do a parametric test. So we're going to go ahead and do a chi-square test of independence. Our assumptions are exactly the same as they were for the chi-square goodness of fit test. Expected frequencies again, the cells have to have at least 5 in the expected frequencies, otherwise we can't even proceed with this test. And now we're going to go ahead and list our hypotheses. Our null and alternative, you'll notice here, are just like they were for correlation. So rho is equal to 0. There's no relationship between our variables. And our alternative is that rho is not equal to 0. So we're already at the point of setting our decision rule. So what's our critical value of chi-square? Exactly how we did goodness of fit test. So what's our alpha level and what's our degree of freedom? So for this test, degrees of freedom is equal to the cross product of our row's degree of freedom divided by our column degree of freedom. So row, the number of rows minus 1, and the number of columns minus 1. So we have 2 rows and 2 columns, so 1 times 1 is 1. And we're going to use an alpha level of 0.05, so our chi-square critical value is 3.841. So what that simply means is when we calculate the chi-square statistic, if it is 3.841 or greater, we reject the null and we conclude that the variables are related. So now we have to find our expected values. So we know our observed frequencies, but what do we expect? if there's no relationship between our variables. And to find that is really, really simple. Whoops, first I have the formula for chi-square, same as before. Chi-square is going to be equal to the sum of observed minus expected frequency squared over expected. We'll get to that in just a moment. So let's get to expected frequencies. Super easy. We simply take the n of the row for every cell. We look at the n of the row, multiply that by the n of the column, and divide by the total n. So let's go to cell A. For cell A, the n of the row was 26, the n of the column was 32, and the total n was 50. So 26 times 32 divided by 50 results in an expected frequency of 16.64. So if there's no relationship between when you read and the grade you get in class, we should see that 16.64 students who read before the lecture got a high grade. For cell B, we have a row frequency of 26 times a column frequency of 18 divided by a total frequency of 50. Again, the expected then is 9.36. For cell C, we have a row frequency 24 times column 32 divided by 50 is equal to 15.36. And then for cell D, column is 24 times row 18 divided by 50 is 8.64. So if there's no relationship between when you read and how well you do in this class, these are the frequencies that we should observe. So now that we have the actual observed frequencies, the actual data, we've calculated what we would expect, we can go ahead and calculate the chi-square. So chi-square is the sum of the observed frequency minus expected, so the difference in any cell squared divided by expected. And what I have here are the 4 cells. Well, that's not very pretty. That's supposed to be a plus sign, and that's all messed up. I'll go back and tell you what that is. So for cell A, the observed frequency was 20. The expected frequency was 16.64. You subtract the 2, you get 3.36. You square that difference and divide by 16.64 to get 0.6785. For cell B, we have an observed frequency of 6, but we expected 9.36 for a difference of minus 3.36. You square that to get 11.2896, divided by the expected of 9.36 to get 1.2062. For cell C, we observed 12, expected 15.39. The difference was minus 3.36. Square that difference for 11.2896. Divide by the expected 15.36 to get 0.73501. For cell D, let's see. The observed is 12. 12 minus 8.64. All right, so 12 minus 8.64 square is 3.36. Squared is 11.2896. Divided by 8.64 is, I think, 1.3067. I don't know why the pluses are not in there. Anyway, so now we have cell A, B, C, and D. You add those all up, and you get a chi-square of 3.9264. You round to 3.93. So we're going to interpret or answer 3 questions. Did we reject the null? Yes, we did. Because our critical value is 3.81 and our observed was greater than that. What's the direction of the difference? We have to look at the data to talk about that, and then we're going to calculate the effect size. So let's first put this in APA. Let's first phrase it. So remember that chi-square can either be a relationship test or a difference test. So you can phrase it any way you want. You can say that there's a relationship between when you read the text and what grade you received in class. Or you can say, among those who get high grades, there's a statistically significant difference between those who read before and those who read after. Okay, you can phrase it any way you want. So what's the direction of the difference? Well, 20 of the 26 students in the read before group, they received high grades compared to only half who read after class. So that's what I'm talking about when you say the direction. So it looks to the student's advantage to read before class. Here's how we format it in APA format, just like we did the other chi-square. So chi-square for 1 degree of freedom and an N of 50 was equal to 3.93. We rejected the null at the alpha level of 0.05. So now we're going to do the effect size. So what is the impact of reading before or after class on your grade? So to do that, we're going to transform our chi-square into something called Cramer's V. Really easy to do because we just go into the data we've calculated and plug it into a new formula. So Cramer's V is equal to the square root of chi-square divided by n times the degrees of freedom. So the chi-square we use is the one that we calculated. So 3.93 divided by the total number of cases, 50, times our degree of freedom, which is 1. So 3.93 times 50, and the square root of that is 0.28. So what does that mean? Well, it depends on what your degrees of freedom is. So we only had 1 degree of freedom. A small effect size would be 0.10, a medium would be 0.30, a large would be 0.5. So we would have a small to close to a medium effect size. So what you want to do is put it all together. Okay, so again, what was the study about? What were the results? What are the meaning of the results? So for this, I would say, the purpose of the study was to examine the extent to which reading before or after class influences a student's grade. And the results of the study indicate that reading before class has a significant positive impact on the student's performance. The effect size is close to a medium effect size. So I think those data suggest that the best thing to do is read before class, right? So this then lends to future research. This was done on a psychology class. This could be extended to other intro courses as well to see if it generalizes. So that concludes our non-parametric chi-square statistics. I think I'm going to have one more video on here just to talk about some other non-parametric tests in general. But if you've got any questions, as always, you can contact me at asikorsky@tamet.edu.